All right, dear students, a very warm welcome to my lecture on differential algebraic equations. I'm Jan Heiland. I'm at the math department at the OVGU. DAEs, that's my favorite topic. That's where I do my research on. Okay, I'm very happy to have you all in this lecture. Of course, I would have liked to meet you in person, but you all know. But on the other hand, I will of course try to do my best so that you both learn a lot here, but also, that might be, no, I won't say entertaining, but yeah, at least it should be lively and it won't be the same all time. Which brings me to the format of the lecture. So it's basically on the website. I hope you have all got the email. And I designed this lecture now more or less from scratch for you, which means that if there is something that you don't like in this format, you just tell me, and maybe I will have changed this on the next occasion of the lecture. Yeah. One thing we could change is of course the language. I personally think that if you're all okay with English, then we should have it in English, because all the research happens in English, and if you can do it, then there's no reason why not to do it in German. Of course, if you have a question and you feel safer with asking in German, then just ask in German. My German is okay. And whenever there is something, there will be consultation hours where we can talk. There will be the live session where we can talk, and so on. But no, let's start with the lecture. Today we talk about I give you an introduction about DAEs, and that it's lecture 1.1. And I also try to keep the slides that I present here and what I write down. I try to keep this in line with the script that you have on the website. But of course, I choose this very format where I have also a lot of writing, because I think that shows best how to work with these concepts. Also, it somehow regulates the speed. So it's also a compromise. There are a few things that are pre-written. You see this here. That's to save a bit of time in between. And of course, if you need a break, then you just hit the break there. But it's also like to have the structure ready. Okay, but enough words about how we do this. Now we start with the real content, like chapter 1, introduction, and we try to answer the question, what is a differential algebraic equation? Okay, I could now just write down an equation for you, but I want to put this in a few words. So differential algebraic equations. Differential algebraic equations are used to model. So they are very powerful for modeling things by means of mathematical equations, to model important dynamical processes. And maybe if you did modeling or ODEs, then typically if you have a dynamical process and you want to have a model for that, then what you write down there, an ODE. So here is this is the by differential equation. That's the differential part. So here the D, this is this D, and differential algebraic equations we will abbreviate with DAE. So this is the D for the differential. That here's the dynamical process. But what's also important, so we model dynamical processes that are subject, means they have to fulfill algebraic constraints, subject to algebraic constraints. And there will be a number of examples so that you subject to algebraic constraints. and here we have the algebraic. So the definition more or less explains the terms. But still we need to somehow understand what is so special, and why there should be a whole lecture, or even better, maybe 2 or 3 lectures on that. And that's why let's look at a few examples. And then I hope this will get more clear what is the differential part, what is the algebraic part, and why both together they make up then differential algebraic equations. So let's have a look at a few examples. And so chapter 1.1, and we start with the free fall. I think you all should have had this in school, or at least we had it in our physics lectures. So this is a ball, and you just let it drop. So here we have the gravity. So there's a force acting on the ball, and well, you all would expect that this ball will just fall down. So say here is the ground somewhere. So the ball will fall down to the ground. It starts here and it will accelerate due to the gravity, and it fall down. Now to do modeling, what is always important is to have a coordinate system. So here we will have the coordinate system. Here this will be the x coordinate, and this will be the y coordinate. The ball, we will assume that it has a certain mass of m, and that's the most important thing. There are of course more effects which we don't consider, and which I think you didn't consider in school too. Like, forget about it. So it's just a ball. Assume we are in a vacuum, and it falls to the ground. And now, what are the equations that will describe the movement, how the ball falls down here? Free fall, and we refer to Newton's second law, which goes like, color good for Newton, which goes like force equals mass times acceleration. This is Newton's second law, and well, that is used to model very typical technical processes. Which means, so we will. So here this will be the force. Force will be linked to here. Here that's the force that we have that acts on here. And mass will be the m here, and acceleration is how this ball will accelerate. And well, in our xy coordinates, here we then have that m times, so here are the coordinates. That's how the coordinates change in time, so meaning they will change in time. So x will change, and x will change, and the y will change. Of course, we already see that basically only the y will change. So mass times acceleration. Acceleration is the second time derivative. So mass times the second time derivative of these coordinates at time t equals the force. What is the force here? There's no force in x direction, so here we have the 0, and in the y direction there is the gravity. Gravity is also an acceleration, and it becomes a force if it is applied to a mass. So here we will have minus m times g. This gives us, well, okay, and and that's the equation. So now we need starting conditions, but then we can maybe solve this differential equation, and then, well, we know how the mass will behave in time. This is still just an ODE, an ordinary differential equation. This is not a DAE yet. Okay, so no DAE. This just then a pure dynamical process where there is no constraints. Of course, there will be some constraints. Latest when it will hit the ground, then there will be constraints to that. But well, as it is now, it's just a dynamical process, and we can use an ordinary differential equation to describe it. So no DAE. How will this now become a DAE? The canonical example that we will use for that is now the pendulum. So the pendulum, how can we draw this? Here we have this point mass of mass m, but now it will be attached to a string, and the string itself, this will be fixed to the ground. So meaning now this will fall down because well, there's still the gravity acting on that, but because it's confined to the string, it will have to move like this way, and it can move that way. So, and that's where these differential and algebraic parts come together. Differential equation, because, well, that's this dynamical process, and it's like this falling ball that we had, but it's now constrained to the strings. And now let's see what can be a model look like here. Again, we will have, so Newton still applies, because, well, Newton applies when everywhere, unless we are very small or very large, but you know, that's like we're here in normal dimensions, so Newton's law will apply. Again, as I said, it's very important to have a coordinate system. We will again use x and y coordinates. So how to model? Let me switch to normal colors again. So first thing again, we have, well, force is m times a, mass times acceleration. But second, circle condition. Circle condition, meaning that the mass will move on this very circle. And here we will have that. Well, I hope you all recall what is the equation for a circle. This means that x of t minus the center of the circle. So here we assume this is the xc and the yc coordinate. So x of t minus c to the squared plus y of t minus yc to the squared. This should be equal to the length, to the radius for the circle, and in this case it is the length of the pendulum. Okay. All right. And well, now we have to bring both of that together. You may already see that this might likely become a differential algebraic equation, because we have this dynamical process here, or these dynamical equations, and this is an algebraic equation, because it's algebraic because there's no time differential involved. Okay, and now how can we derive the equations to that? And one possibility is to use the Euler-Lagrange formalism to derive the so-called Euler-Lagrange equations of motion. There's also, if you look into the script, it looks very much the same, but there you will have a link to this Euler-Lagrange equation. how they formulate it in more general concepts. Okay, so this is now important, the Euler-Lagrange. For that, we will need the Lagrange function. So for that, the L function, Lagrange function L, and this is defined as the okay. Sorry. Now we do this the other way around. Oh no, we have it here. So the Lagrange function for a constraint movement is defined as L to be the potential energy, U minus the kinetic energy. So if there was only U minus T, this is an unconstrained, meaning that the potential and the kinetic potential and the kinetic energy, they should be zero or a constant, meaning they won't change in such a system. But now we have a constraint to here, and for that we need the so-called Lagrange multiplier that includes the constraints. Okay, L times H. Now let me quickly explain what are the terms here, particularly for the pendulum. So the U is the potential energy. And for the pendulum, this is just the mass times the G times the Y. So okay, think of the Y means how far we are up here. If we are high, then the mass will be high, the energy will be higher, the potential energy. There's the G that defines how much energy is there because of the force that acts on it, and there's the mass. So if there's more mass, then we will have more potential energy. Then there is the T, which is the kinetic energy, and for the kinetic energy, and for the pendulum, it's the energy that is in the that comes from the movement. So if this moves fast, then it has a high kinetic energy. Movement is the first time derivative, and in this case, it is a half times the mass times x dot t to the squared plus y dot t squared. Okay, and then the lambda is the multiplier, and the h is the constraint. And in this case of the pendulum, this is I have an infinite blackboard here. So here the constraint is h. This is no, that's not so nice. So this is the constraint. I will write this constraint once more on the next slide. We will need this. Okay, so this is the Lagrange functional, and let's work on with the constraint. H is in this case L squared minus what was over there, so x of t minus xc to the squared minus y of t minus yc squared. So the constraint was that this x and the y should always be on the circle, so equal this length, and we can rewrite this such that or in verbs. One will need h is 0 if and only if x and y on the circle. That is how this constraint is defined. So this is just the verb is how one would describe it. Okay, but now we have this Lagrange function now, and then from the D'Alembert principle, so let's call the D'Alembert principle. Well, that's not the basic content of this course. I'm just dropping these names, and if you're interested in how this modeling works, then you can look all this up. Equations of motion. Equations of motion derive from these d by dt dl by dq dot minus delta l dq is 0 for q is q1, q2, q3, and so on, the generalized coordinates. Okay, so now for the pendulum, let's go back to this pendulum color. Pendulum, we have that the L is a function of x and y, and what other parameter we have here, and the lambda. So these will be the meaning that q will, these are the generalized coordinates of our Lagrangian, and then one can compute these derivatives, and then one ends up in the system of equations. I see there's an error in the script. I will fix this as soon as possible. But with this principle, one will end at x double dot of t is equal to minus 2 lambda x minus cx. That's nice. 2 lambda x of t minus xc. Y double dot of t will be the same as minus 2 lambda of t. Lambda depends on t2 times y of t minus yc minus m times g times y, and the other equation will be x minus cx to the square, and so x of t minus xc to the squared plus y of t minus yc to the squared minus l squared. So that's the other equation, and that's actually a very nice example for a DAE. This will get a label, so I will refer to this in the script. And so it's a nice example because of many reasons, but one reason is that it's here one very nicely see this is the A part, so to say. This is an algebraic equation, no time derivative in here, And this looks like a dynamical system. So mx double dot is 2 times xt minus xc. So this looks very much like this here. Mx dot is something on the right hand side. Well, if it wasn't for this lambda which is in there, so it's not pure, but well, it's very safe to say that this is the DA, the D part of this equation, and this is the algebraic part. Alright, then do we have still time for, shall we do the electrical circuits? Okay, maybe we skip the electrical circuits, have a look in the scripts. Maybe I will just write down the equation, because that's an equation we will work with as well. So there will be, so please check the script. Well, if we have electric engineers among us, then well, please write me, then maybe have an extended exercise on that, so please check the script. But what will come out here is this kind of equation: cx3 dot t minus x2 dot of t will be minus x1 minus x2 over r. C and r, these are constants that describe this electrical circuit. Okay, I will draw the electrical circuit just for completeness. U x1 minus x3 minus u. This is one equation. That's basically Kirchhoff's law of nodes. And here this is the grounding. Okay, this is the model of such a circuit. Let me draw the model. Let me draw just to have it all on one page. This was a very simple circuit with a resistor here. So this is the R. Here is the R. Then there was a capacitor with the constant C. Here one can apply a source, and then this goes through a resistor and here into the capacitor, interacts here, so this will give you a dynamical system. Here that's the I don't know what was the it's formulated in the potential. So x3 is a potential, x1 is a potential, and here's the potential that you will observe on x in this part. And those, well, that's the model for the circuit. And this DAE is interesting, and we will make use of that because it's a linear DAE. That makes it interesting. I should not be that lazy and omit of t all the time. This can also depend on t. This can depend on t. Yeah. And again, so these are obviously algebraic equations here. These are obviously purely algebraic equations. And this is, well, here we have the time derivative. So this is a differential equation. Well, but it's also a bit mixed up. So one equation for these two differential parts. Well, so it's not a completely obvious how this DAE structure looks like. Okay, but we won't work a lot with these ordered models, but this type of equation, that's an interesting thing because there's a lot of theory to that. And now very quickly on my favorite equations where I do a lot of research is Navier-Stokes equations. They are used to model flows. They model flows, and this can be, for example, well, a flow through a channel. So assume this is a channel. Here the flows comes in, and here the flow exits again. here there is walls, and well, it just flows through here, but it interacts with the walls. There it's stopped, so there will be dynamics happening in here. And these equations, the model for that will be equations that describe the model flows via the velocity v, which maps a time interval, so say 0 to t times a domain, it's often called omega, maps into the r, depends, no, maybe r2 or maybe r3. Okay, here that's the domain omega, and the v describes the velocity of the flow that enters here, and so on, via the velocity and via the pressure. If you know how the pressure looks like, and if you know how the velocity looks like, then you know what the flow looks like. Let me maybe, if this is a particular color, so this all here is the omega times the omega, and also the pressure. It depends on time, but it also depends on the space, and it maps into the r. The pressure is just a value, and the velocity is a field. Via velocity, and the equations dv by dt. Now I leave out the arguments. V, such a Kronecker product. This is the spatial derivative, the Nabla operator times the V. And there's the Laplace operator, which is also a spatial differential operator. And there's the pressure gradient. So this is the Nabla applied to the P, equal to 0, or maybe a force. And the other equation has that Nabla and the inner product. So here's the divergence. This should be 0, 2. And now think of, well, there's no theory of PDEs and abstract differential equations, but think of the velocity taking a time and returning a function that depends on the space. So this can be, or this little thing is more or less the v dot. Well, it's the time derivative of the velocity. So this here is our D equation, and here we don't have a time derivative, we only have spatial derivatives, but we talk of dynamics, and dynamics is meant with respect to time. So this here will be the A equation, and that's why the Navier-Stokes equation will occur as a as an example for a differential algebraic equation throughout the lecture. Okay, so much for this example, and okay, there will be even another example, the example on automatic modeling. I also call this sometimes engineers versus mathematicians. Because this is an approach that it's very convenient for the engineers to do modeling, and it leaves all difficulties, as I would say, to the mathematicians, well, to then solve these equations. How does it work? Well, think of, okay, do I have a picture for that? No, not really. Well, think of a very complicated process, say, okay, maybe that's, think of a piston, cylinder in German, and well, and then this goes like this, and here is what is called Kurbelwelle. I don't know what this is in English. So that's a part of a motor, and you see there's very many processes in here. So here there is ignition. Here is something that explodes, and here this rotates, and this piston, it goes up and down, and that's somehow a very complicated process if you want to model this, have this in one model. But what you can do, so say this is process, so this is well, one thing that you observe here, things rotating. Say this is process sub-process B, which is this going up and down, and what's happening in here is this is sub-process C. And what you now can do is have equations. So say one equation system for A. Second, you have maybe an equation system for what happens in B, A, B, and then you have here you will certainly need a PDE, because well, there's very many things also spatially distributed happening. Well, you will need one equation system for that. Okay, now you have modeled this all. You have an equation for that, you have an equation for that, you have an equation for that. Plus, so and now this makes, this here all might be just differential equations, or partial differential equations, plus conditions that link A, B, and C. Let me say this once more for you. You have an equation system for the A, which might be maybe differential equation. You maybe have a equation system for the B, which might also be just a differential equation. And you have a differential system, an equation system for process C, which certainly is a partial differential equation. But you see the D here, so it's a differential equation. But then you need to combine these, saying, for example, whenever this value is like this, then this value, so the angle should be like that. And this is well, equating this with this, meaning that these conditions, they will very likely be algebraic equations, because they you just equate, as I said, this position, you equate this to an angle that is in the system. Okay, meaning the engineers, he takes or she takes 3 equations for their subsystems, and then they just put it together, and what they get is, well, a system of differential equations and algebraic links between the equations. Okay, well, so much for the examples. Now just a few quick words. Why are DAEs difficult to treat? And I just make a few points here, and then we can talk. In the wrap up on Friday, I will have the examples for that, and it's also in the script. So why they are difficult? DAEs have non-smooth solutions. Well, let me have this very let's do it right. So why are they difficult to treat? They have possibly non-smooth. They will very likely have non-smooth solutions. Have a look at this example. So x1 of t, x2 of t, and 0 is x2 of t minus g of t. This means if g well, this means that if g is a C0 function, a function that is just continuous but not differentiable, then this will mean that x2 is a C0 function, but x1 will be a C1 function. So this will be a C1 function. Now you may say, well, there is a smooth solution, but x2 is not smooth. It's only continuous but not differentiable. And even worse, so that's really a problem. Even worse, and we will have examples for that. DAE solutions may depend on derivatives of the right hand side. So if you think of ODEs, then you have this integrating behavior, and this is very easy. There you have good there you have good methods for that, because well, integration is a numerical well-posed thing. But if you have differentiation in your algorithm, then this will always mean problems. And from here, difficulties to expect the numerical treatment are twofold. Generally, the smoother the solution, the better for the scheme. We will talk of that, but if you want to solve a differential equation by a numerical scheme, then a very basic condition to that is that the solution is smooth. And if the solution is smooth, then you can use high-end numerical schemes, and then everything works fine. But now, well, we know that the solution won't be smooth. So we have parts that are not smooth. So this is not smooth. Not smooth. This is just continuous. Okay, so one problem that we can expect here, and the other problem is another basic problem. Numerically, and this always holds, differentiation is hard, integration is easy. Okay, and that's also so differentiation is nothing that you want to do in a numerical scheme. Integration is nice because, well, then errors will smooth out, and differentiation is bad from a numerical point of view. And well, as I said, the solutions will depend on derivatives, so there might be a differentiation involved, and well, and this will always mean it's difficult. But this also means for lots of interesting and relevant. So that's also always important. These DAEs, they really play a role in modeling things. So lots of interesting and relevant questions that we will address. And we go on with that in the second lecture. So much for today. Thank you.